So our first speaker will be Trevor Rhone. So we're in for a treat. I've known Trevor for quite some time. He's had a pretty impressive career where he's roamed from Japan to Harvard and now is a professor at RPI. He is coming up for tenure soon. And he's going to tell us about some of his amazing work using AI to accelerate materials discovery.
Thanks, William, for that really kind introduction. It's really a pleasure to be here. Thanks to Bill for inviting me and putting this wonderful event together. It's really fantastic. Can anyone guess what this image is? I heard graphene. It's close. It's a 2D atomic crystal. This one is actually not graphene. Of course, you really can't tell just by looking at it. It's a computer rendering of a traditional metal halide. That's actually a Janus traditional metal halide, and this one is magnetic. And also, it's a cover article of a paper that came out last year from my group in Advanced Theory and Simulations, and we're very excited to share some of this work with you. So the title of the talk is AI-Guided Materials Discovery of van der Waals magnets. And I'm at RPI right now, although this work started when I was a postdoc here at Harvard. Now, although the title is about AI-guided discovery of van der Waals magnets, what we can really ask is a bigger question, which is the following. Can we design new materials to accelerate advances in quantum computing and quantum communication? So I'll try to answer this question towards the end of the talk, although we'll focus mostly on 2D magnets in the beginning of the discussions. So in particular, can we look at new materials that will accelerate the abilities to do work in quantum computing? Can we find new superconductors, for instance, for implementing quantum computing research? Superconducting transmon qubits in particular, or perhaps even linked to the work that Serena talked about earlier today. Can we find new materials, such as materials with interesting defects, to support existing technologies and accelerate the technologies of the future for quantum communication? And also, can we make some device by creating some new material that is able to couple qubits for creating the world's first global quantum internet? These are the questions we'll try to answer today. Okay, and we'll try to do this work with the following materials informatics. That's combining experiments alongside theory in the form of digital data, including statistical methods and computational tools to accelerate quantum materials discovery. Is that my phone? It's on airplane mode too. It's very strange. Huh. Okay, sorry about that. Siri is very excited about my talk as well. Okay, so quantum materials discovery. We want to accelerate this material discovery. Okay, and put things in some context. I'll typically use AI and machine learning interchangeably, although machine learning is a subset of AI which intersects with data science, which comprises databases, data mining, data visualization, and also statistics. I like beginning with this slide. And so these quantum materials really take advantage or exhibit emergent phenomena. And this slide is from a paper by P.W. Anderson titled More is Different. This is an electron. It has some spin. This is a collection of electrons. And the idea behind this paper is that a collection of particles is more than the sum of its individual components. And the idea for AI is, can you take one of these components and predict something about its collective behavior without really knowing in advance the behavior of the collection of particles? So for instance, can you inspect just one electron and predict something about the emergent charge order or spin order? For instance, can these electrons all align to exhibit Farabitic ordering? And under what conditions can this happen? Can AI help us to figure this out? Now, these electrons can live in 2D atomic crystals. This is chromium triiodide, chromium germanium telluride. In 2017, they were shown to be down to one layer of chromium triiodide, intrinsically ferromagnetic. This was the first time this was done. This was very exciting. So it happened that, a speaker from earlier in the week, Pablo Hierro, did some work on chromium triiodide. It's very exciting at the time, and still is. And this work over here by folks on the West Coast on chromium germanium telluride. Now, it so happens that I was a postdoc here at Harvard in 2016 doing experiments on this material, chromium germanium telluride, in particular ferromagnetic resonance experiments. And I didn't get a Nature paper, unfortunately, because I had issues with my experiments. There were two. One, this material is a bit air sensitive. It would fall apart after I took it out of my cryostat. And the other thing was the resonance of chromium germanium telluride, or CGT, was a bit outside the range of the equipment that I had. So I wanted to have a new 2D material which was magnetic, but had different properties than the ones I had already. And I talked to Pablo at MIT, who was working on this one, and he said, well, this is even more air sensitive, so this sort of started my computational study of 2D magnets, and searching for new 2D magnets using a combination of computational methods, first principles calculations, and AI. And by the way, these are magneto-optical Kerr effect spectra showing that down to one layer is ferromagnetic, down to two layers below the Curie temperature is ferromagnetic. Okay, so an outline of the talk. We'll start with the motivation. Why are you here? Why should you listen to me? And then we'll talk about, in particular, challenges for materials discovery. Then I'll try to answer or address some of those challenges using materials informatics. I'll tell you what that means in a bit. And we'll focus on a case study, which is for 2D magnetic materials. All right, so why do we study magnetism in two dimensions? One is this emergent phenomena, which I alluded to before. This is a paper by P.W. Anderson. The next is the so-called Morman-Wagner theorem. The idea there is that a long-range magnetic ordering should not exist in two dimensions unless something breaks the symmetry. In this case, there is this magnetocrystalline anisotropy that breaks the symmetry. This means that the magnetization prefers one direction versus the other, and that causes a long-range ordering. This is potentially interesting because there could be an interplay between dimensionality, number of layers in a 2D material, and strength of the anisotropy, giving rise to potentially interesting spin degrees of freedom. And the other thing is some applications in data storage. So this slide here, I'm borrowing from our friends at IBM Research, and this is talking about advances in MRAM, or magnetic random access memory. And the idea is, for this is, the key idea you should take away is that advances in materials drive technological innovation. So let me illustrate why that is. So in the 70s, this idea for MRAM, which you heard about earlier today in the talk of Professor Jacob Gales, if you have different spins, they can code zeros and ones. And the first time it was done in the 70s, it could only happen at cryogenic temperatures. Then there were some advances in materials, so you could then do it at room temperature. And then many years later, they changed the material for the tunnel junction. Then it increased the read speed. And then later, the spins went from in plane to out of plane by another materials advance. And you can increase the write efficiency. And then you have a technologically viable material. But it took over 30 years from this point to that point. So wouldn't it be nice to have some way to go from 30 years to 30 months or 30 weeks or even shorter? And that's what we'll try to tackle in this presentation. So, but we know, why is this so tough? Why is materials discovery so challenging? It's the following, you have to find this particular material that can be tough to calculate or to measure. Then often you have to have multiple criteria being met. So for instance, if you want a magnet, if you want to do something in like an industry, in a lab, something practical, it should have a Curie temperature above room temperature. So those are two criteria that you need to have met. And the search space you have is really enormous. So this paper suggests that the number of materials that could exist in the universe is 10 to the 100. This includes small molecules, large molecules, and crystal structures. And this number, 10 to the 100, is equivalent to the number of particles in the observable universe. It's really a huge number. So I like making an analogy between exploring chemical space and outer space. It's clearly quite challenging. Okay, I made a mistake. All right, so I have a question for you. Now, Nope. Pre-summer 2023, if you wanted to find something and you didn't know the answer, what would you do? You would Google it, exactly. How did you know? But no, what if you asked Google, give me some undiscovered 2D magnets, what do you think would happen? You would no result, maybe you would start smoking and they would blow up, something like this. Amazon would show up, yeah. So there's probably won't work so well. So lucky for us, asking Google something that it doesn't really know, it's tough because it looks up in the database, if it's not in database, well, you have a problem. Well, lucky for us, there's some key advances in AI, which could help us potentially overcome these challenges. One which was really exciting last fall is this introduction of ChatGPT. It's OpenAI's generative pre-trained transformer. If you haven't heard of ChatGPT, it's essentially a human-like chatbot. You can ask it questions and it gives you human-like responses back and has lots of information, which sometimes is quite useful, sometimes it can lead you a little bit of a strain. But I like to argue that the way this works, it encodes text as input to the AI. And how this text is encoded is really important for making this a success. And we'll use some of these ideas, encoding data in a special way, to make the model successful later on in today's discussion. Okay. Another cool thing about AI is it can really do exciting things that we couldn't do 20 years ago, such as this model, You Only Look Once, which does image recognition, or YOLO. And this is a set of images that changing with time of video. And the model classifies the objects in the image real time. It's really exciting. Also really enjoyable just to watch this go over and over again. But okay, why am I showing this? So if an AI can do this for images, can it identify whether material is insulating or metallic by looking at crystal structure? That's one of the things we like to ask. In particular, can we take a graphene and, without doing a calculation or measurement, tell, just by inspecting the lattice and the chemical composition using AI, tell whether it's metallic or not, or MOS2, tell whether it's semiconducting, or these chromium germanium telluride, chromium triiodide, tell whether they're magnetic, and this one here, tell whether that's magnetic topological insulator. Okay. So we'll use this materials informatics to try to tackle these questions. In particular, we'll focus on materials informatics for knowledge discovery, focusing on 2D magnets, their chemical stability, and magnetic properties, and hopefully we'll get some interesting physical insight also from using the analysis of the model. And we'll focus on ferromagnets just because we can pick a target, although this could be also anti-ferromagnets. All right, so materials informatics, I mentioned a little bit before, it's a combination of AI and material science, where the AI is approximating some function f of x, 1 through xn, or these x1 through xn, or things that you can look up in a chemical table, or easily calculate or easily measure, like the number of unpaired electrons, or the ionization energy, or number of valence electrons of a constituent chemical element. And it maps that to something that's hard to predict or calculate, such as a magnetic moment, y. And the nice thing is that this function can be evaluated very quickly, in milliseconds, much faster than taking time to do an experiment or calculation on a supercomputer. Another thing is, why do we want to use materials informatics? Because this n here can grow quite large, hundreds or thousands of dimensions. Or human brains can understand patterns in 0, 1, 2 dimensions, 3 dimensions. We can see patterns on the page and understand the text. We can see me moving around the room and understand patterns in 3-dimensional space. But can you understand the patterns in a 4th-dimensional hypercube? It's quite tough. Even for me, it's quite tough. Well, for me, it's pretty much impossible. Maybe you can do it. But a machine can quite easily do it. It doesn't really matter the number of dimensions. It can identify patterns in a high-dimensional space. This case is not necessarily spatial dimensions, but descriptor space, where the descriptor is the input to this function, or the AI model. Okay, so why else do we want to use some AI to guide the study of materials? We talked about the material source space being huge. For instance, ICSD has over 200,000 entries. The Inorganic Crystal Structure Database. There's also the Chemical Abstract Service, which has over 49 million entries. We talked about the virtual chemical space before. So if you're looking for one material of interest, doing serial calculations or experiments, it's going to be really slow and really, really very quite expensive. So we need another way. Okay, so I also made another mistake. So now what I'd like you to do is help me make this talk work. This is going to be kind of emergent properties happening here. So I'd like you to take a moment and close your eyes. Really close your eyes. It's going to be fun. Take a deep breath in and travel back in time and space. And let's go to ancient Greece. And now open your eyes. And you're a Greek philosopher living in ancient Greece. And this is a picture of Plato. And you're an alchemist, and you know about a small set of chemical elements. You know, for instance, there's iron, manganese, magnesium, hydrogen, air, fire, water, earth, helium, and so on. Okay, you're ancient Greece. Now, because you're Greek and you thirst for knowledge, you want to understand more about the chemistry of these elements. So you say, well, what is a good descriptor to describe these elements? That's going to be atomic number and not say color of the elements, because you're clever. You can choose the rest of the right way to describe the material. And then you ask yourself the question, how can I understand the trends in the data? And you say, well, let's choose the descriptor of the atomic number and apply a model. In this case, it's a sort. The atomic number is in increasing order. And if you do that, you get the following. You have hydrogen, helium, lithium, air, fire, water, earth, beryllium, carbon, and so on. And what's the pattern that you notice in these data? With respect to the atomic number. I heard someone say integer. It's going up by integer 1. So with this key pattern that you extracted from analyzing the data, you will probably realize that this air, fire, water, earth aren't really chemical elements, so you take them out. And also, there's something between 6 and 8, which is 7. And what is at number 7? Nitrogen, yeah. You guys are very clever. Usually the physicists don't have an answer for that, but you answered really. We have chemists in the room. There were chemists in the room. That's wonderful. You answered it really quickly. Thank you. Excellent. So of course, this is a familiar idea to you. This is not something new. But if you keep playing this game, you can get all the chemical elements out, and the patterns in the column number and rows give some insight to the elemental properties. Now, this is familiar, but the question is, can we do something similar for crystal structures? So this crystal structure here can be one of 3 things. Does anyone know or can guess what it is? Al2O3. That's a good guess, but it's not. It's something else. It is. It's carbon, exactly. So it's lattice of carbon atoms. But you may think, well, it's not what I'm typically thinking of lattice of carbon atoms. It's just diamond. But diamond doesn't usually look like this. And in this case, diamond has a defect. We talked about it earlier in the conference. It has a nitrogen vacancy defect, where you place carbon with nitrogen, a neighboring site is vacant, so it has this NV center defect. And if you have enough of them, you get this pretty red or pink color. So there's a relationship between the structure of our material and its property. In this case, there's a defect, and it gives rise to some change in the optical properties. And we would like to learn this structure-property relationship using AI to be able to make these kinds of predictions, mapping the structure to the property of the material. One of the things that got me really excited about doing this kind of research when I was a postdoc is this paper here. They would take a set of transition metal alloys that are either ferromagnetic, these open squares, or non-magnetic, these closed squares. And they're plotting this on available atomic volume and calculated chemical hardness. This is not a mechanical hardness. It's more like a compressibility, or d mu dn. And you notice if you zoom in this portion of the graph and blow it up, there's a really well-defined region of only ferromagnetic transition metal alloys. So let's say it takes you a day to calculate or measure one of these alloys, and you have a new alloy there. It falls in this part of the graph, but you don't know whether it's ferromagnetic or not. What would you guess it is based on the pattern in the data? Did you have your hand up? Yeah, it's probably not ferromantic. Yeah, it's good. Yeah, that's exactly right. It's not ferromantic. And if it were here, then it would be ferromantic. Yeah, you got it right. So your brains did some pattern recognition to identify the patterns in the data to make the correct predictions. We would like to do this kind of automatically using a machine learning model. Okay. So one question which we haven't talked about too much is, in this paper they chose atomic volume and chemical hardness, but what is a good descriptor for a machine learning model? How do we choose this x1 through xn? That's something I'll come back to later on. It can really affect the outcome of a model of prediction. All right, so let's take a segue and talk about the mechanics, if you will, mechanisms, the theory of machine learning a little bit. In machine learning, you need three things. You need data, descriptors, and also, of course, statistical models. And these days, there are lots of databases that are readily accessible. So machine learning for materials is becoming more and more popular. You have people spending their careers building very nice mathematical representations of materials, or these chemical space descriptors, examples of which include the Coulomb kernel, bag of bonds, smooth overlap of atomic positions, or SOAP, which we'll talk more about later. These ones based on graphs, such as CG, CNET, and Align. Align is actually coming out of NIST, which is a very nice machine learning model. And the data science tools exist, readily available, so scikit-learn, Google TensorFlow, PyTorch, other things coming out of Google as well. It's a really good time to be a material scientist or chemist or engineer and working on these kinds of problems because the tools are readily available and quite powerful. So for data, we have materials projects, AFlow, C2DB, LQMD. This is one of my favorite because it's focused on 2D materials, ICSD, MatNavi. I was actually a postdoc in Japan when I came across MatNavi for the first time at the National Institute for Material Science. And Jarvis, which is also coming from NIST. IDA, which is, I think, run by Boris Kuczynski, who's actually here at Harvard, although they're also doing kind of workflow management. And the Materials Cloud, which is coming out of a group by Nicola Morsari at EPFL. Wonderful, wonderful group to visit. Okay, so there's descriptors as well, the second element or framework for machine learning for materials. These are ways, again, of mathematically representing the materials. These could consist of the atomic properties of the constituent elements, or some clever mathematical representation of the crystal structure, like SOAP, for instance, or representations learned from data, which we'll talk a little bit more about later today. And one really simple-minded example, let's say you're looking at the data set of ionic compounds. You'll notice that your compounds comprise different columns of the periodic table. So perhaps you can guess a descriptor that is the column number for your study. Okay, and then last but not least are the statistical models. Ones that you're familiar with are these linear regression models. So if you've done linear regression before, and all of you, I could bet good money that you have already done machine learning, so congratulations. But they're more sophisticated models like these nonlinear neural network models that are universal function approximators, the ones that we used to do image recognition in YOLO earlier in the presentation. And these are more sophisticated ones that are also quite nice. So the typical material discovery framework, we have some large set of candidates that we want to choose from. We screen by first principles calculations. And then the best candidates we screen by experiments. And hopefully in the end, we have a nice set of materials that we want to build our devices, develop our new technologies. But what happens typically is this is a slow process. And this is even slower. And in the past 5-10 years or so, AI has really become something that people use to accelerate both stages in the material discovery process. AI is fast and it's inexpensive, although it has typically lower accuracy and needs some data to train the model. Even though it's been quite popular and successful in some areas, there's still a lot of challenges that remain. One is the need for accurate data sets and also lots of labeled data. And I'll explain what I mean by labeled in a bit. And so the solution I'll propose in the main part of this discussion is so-called semi-supervised learning, which is combining supervised learning and unsupervised learning, which I'll explain a bit more about in a bit. Okay, so first let's dive into kind of the physics and talk about our database created by our simulations. This is of traditional metal halides. This is a traditional metal halide based on chromium triiodide. This is a crystal structure. The chromium atoms sit here at the A sites, and the X atoms sit here, so above and below the plane. And we can make, at different A sites, different traditional metal substitutions, and for different X sites, different halogen substitutions. And if we do that with all the possible combinations, we get about 10,000 combinations. We choose about 700 to inspect with the DFT, the density functional theory, or these first principles calculations. This took about 2 years with 700 calculations, so it takes quite a while. With 700, you can then go ahead and use AI to inspect the rest. And because we're looking at magnetic properties, we have to look at the ferromagnetic order and also anti-ferromagnetic order. For instance, chromium triiodide is ferromagnetic, but iron trichloride is anti-ferromagnetic. So we need to consider both in our calculations and pick the ground state one to add the label for magnetic order or magnetic properties. And this is an example of the data. So this is A1 substitutions on the horizontal axis, A2 substitutions on the vertical axis. In this case, both X sites are iodine. For instance, this is chromium 2. This square right here represents one material, triiodide, and it has this light orange color, so it has some large magnetic moments like magnetization, saying that it's ferromagnetic. Notice that there are some gray squares. These are missing data. So the data that are missing are unlabeled. They don't have a label for the magnetic moment. Data that have some color here are the labeled data where there's a DFT calculation that's been done. Now, we don't only care about magnetic properties. We also want to make these things in the lab eventually. So we use the formation energy as a 0th order approximation for chemical stability. And the results for the formation energy are here with, again, A1 substitutions on the x-axis, A2 substitutions on the vertical axis. This time, the X sites are mixed. They're chlorine and bromine in this case. And the color now represents the formation energy. And again, the gray squares are missing data. So we have lots of data to train our model, but first we have to make some mathematical representation of the data. We use this SOAP kernel, or smooth overlap of atomic positions, to create our mathematical representation. And I won't get into too much detail about how SOAP works, although you feel free to ask afterwards if you like. And the idea is we have some fingerprint for describing the material. It's some long vector. And if you project this long vector into 2 dimensions, this page here or screen, then you can see how it behaves. And it tends to cluster with crystal structure. So each dot is a crystal structure or a material. And all the crystal structures that are diamond are in this part of the chemical space. And all the hexagonal structures over here. And each one varies by chemical composition. So the SOAP encodes crystal structure and also chemical composition. And we'll try to use it as a way to describe our materials and check to see if it works in the end. Okay. But there's a problem with SOAP. SOAP tends to be very high dimensional, too high dimensional for us, given the number of data that we have. So in this case, we have 98,000 dimensions. So the vector has a length of 98,000 entries. And that's too big for us. So we compress it using principal component analysis, or PCA. So our input down to 220 dimensions. So our input is going to be this PCA compressed SOAP descriptor, which is passed into a function, which is approximated by an AI model, which then predicts things like magnetic moment or formation energy, which is the Y value. Okay, so our model is one based on semi-supervised learning. It combines an unsupervised model, such as autoencoder, shown here, with a supervised model, such as one here, a feed-forward neural network, which performs the labeling task. And the nice thing is, if you couple those two, you get a semi-supervised learning model. And essentially, you train an autoencoder. This basically takes X in and X out. And you try to compress this. It works a bit like image compression or audio compression, but for materials data. And this compressed version of the material gets passed into this input for the second model, which then tries to learn the formation energy or the magnetic moment. That's the Y hat. Now, the cool thing here is that you can add data which don't have labels. So you don't have to do a DFT calculation. And you can improve this part of the model that improves this representation, which then gets passed into this and improves the performance for this prediction. And I'll try to show you some evidence for that in a few slides. Okay, so this is a kind of a cartoon. We have some training data. In this case, we have the 6 points. Let's say each point took us a month to measure or to calculate. And we can then fit this to a line. So we learn M and C, or coefficients of the model. And then we can compare or model prediction to these red squares, the unseen data or the test data. And if the model matches the test data, then a model can generalize and it could work well for data the model hasn't seen before. So it's kind of trustworthy in this case. Now we can do a similar thing for a model. So we can tune all the coefficients by taking training data, then compare it to the test data. And in the end, we get for the magnetic moment, the horizontal axis has DFT calculated magnetic moment. The vertical axis has the machine learning predicted magnetic moment. This dashed line, this guide to the eye, is a perfect prediction line. And that line shows, well, if the points fall close to this line, it shows that the model is performing pretty well. And for our training data and our test data, the points are fairly close to the line, so the model is performing pretty well. It can predict magnetic moment. So we're happy with the performance there. Again, because we don't only care about magnetic properties, we want to also make these things in the lab one day. So we care about chemical stability. We will plot the formation energy as a proxy for the chemical stability. And again, all the points are falling close to this perfect prediction line, so the model is performing pretty well. And now, recall that it took us about 2-3 years to calculate these 700 materials. Well, we can predict thousands of properties in milliseconds once a model is being trained. So it's really, really quite nice. So I promised to show you that if we add unlabeled data, so we can add data. So the crystal structure exists, but we don't know what its properties are. If we add those data, then we get an increased performance. So we go from 0 unlabeled data, but 700 labeled data, performance of about 0.2 R squared, which is not good. And this, adding more unlabeled data, we go to about 0.8, which is actually pretty decent for a machine learning model. And so it works. It's actually pretty, almost magical. But the magic happens here in the autoencoder because unlabeled data make this part much better. And this part that's improved gets passed into here, which can then do a better job of predicting the magnetic moment and the formation energy. Okay, so we can start from 700 structures and then predict thousands of structures. Then in the end, we can say, well, I want to pick the one that has large magnetic moment and quite low formation energy. It's chemically stable. We can screen the materials for the ones that are kind of most promising for synthesis and characterization with experiments. And we have a short list of materials that are potentially promising for that reason, although we haven't done the synthesis or experiments yet. If you'd like to, please let me know. We should talk some more. But because the predictions are matching pretty close to the calculated DFT values, then we're pretty confident that the model is working fairly well, at least for giving some direction for finding useful materials. Okay, so we have taken a set of 700 A2X6 transition metal halides, trained a model to predict on thousands of potential A2X6 monolayers, transition metal halides. We can then identify those with large magnetic moments and low formation energy or high chemical stability, and then find the ones that are most promising for further investigation. We can also adapt this approach to other van der Waals materials, not just monolayers, but also multilayers, bilayers, trilayers, and also heterostructures, which I'm really excited about. Why? Because if you look at heterostructures, the space of candidates, even if you just look at the transition metal halides, becomes quite large. It becomes 10 to 26. So we really need a guide to help us figure out what to look at next. And our guide is going to be the AI. So from monolayers to heterostructures, we have this huge space. And maybe one day, all this is really hard, is to tackle this twisted materials. I can't do it yet, but maybe one day it'll happen. But it's a pretty exciting thing to think about trying to do. Okay. Also, we can start looking at other properties such as spin textures, topological properties, and superconductivity. And there we start answering the question we started with the beginning of the slide, which can we find new materials to support advances in quantum computing and quantum communication. And we haven't done it yet, but we started in all these projects, and things look pretty promising so far. So stay tuned for next year when we have some nice concrete results on that front. If you'd like to learn some more about the research, please take a look at this QR code. It takes us directly to the paper that most of the work is talking about. And I'd like to thank the funding agencies, Access, Exceed, ALCF, and also NSF Career Award for their support. If you want to learn more about the group, please visit this website. This is the group website. And I'd like to thank, most importantly, you for your kind intention.
All right, it looks like Jacob's up with the first question.
Very nice talk. I just have a question. I'm stupid. I didn't understand the autoencoder part.
Oh, okay. No, it's a tricky part to.
How does you just inputting the crystal structure?
Mm-hmm.
What information is it bringing in that makes it better?
Yeah. So it that's a good question. So it compresses the information, and if you just had the autoencoder, you have a compressed representation. So imagine like JPEG compression. You save your JPEG, it gets compressed on your computer, then you can unpack it to look at it, but you save space by compressing it. This is also compressed, but a representation of the materials data. And you say, well, it's compressed, so does it make it better? Well, because it has fewer dimensions, it may be better because we have fewer data points, and it's easier for the model to fit to those fewer data points with a smaller sided descriptor. Imagine fitting 100 data points to a 100-degree polynomial. It's just not going to work. So you want to have to map with your number of data points, a fewer descriptors to make it more reliable fit in the end. The other thing is, which is maybe a better answer to your question, is that these two models are coupled. So it's coupled, the loss functions are coupled. So when it's reducing the loss, it's tuning the parameters to train these coefficients to not just reduce the loss between x and x decode, but also with y hat. So the latent space is kind of learning a representation that best matches predicting these formation energies and magnetic moments.
So Jacob, is your question about autoencoders in general or autoencoders in this context?
I'm still confused. If I can maybe reframe it, is it that like you have some model, yeah, and you want to bring some new data in, but it feels like you have an X but no Y.
Mm-hmm. Maybe this is another way to think about it, right? Which is, let me think if I can say this, right? So imagine, for example, that you are considering yourself in the era of Tycho Brahe and Kepler, right? And you have lots of observations of heavenly bodies. And you have, okay, here's a heavenly body, it's at this position, it's at this time. Here's some other heavenly body, it's at this position at this time, right? So you have this collection of data, right? But as physicists, we know that Kepler has a simpler representation of this where he says, well, if you give me, like say 3 parameters, I can basically go and reconstruct all of these curves, right? So there's a more compact representation of the information than the actual trajectories of the planets, right? So in some sense, you say that a model exists, and then you start from there to operate in the model space. So if we think of the autoencoder as like this sort of general function approximator or neural nets in general, right? Then by doing this autoencoding process, you're trying to find if there is some simpler model that actually exists. And then he can work in the space of that simpler model. But maybe this is an offline discussion.
Well, then my next question would be, what happens when you add unlabeled data that's incorrect?
Well, incorrect in the sense that DFT sucks, or incorrect in the sense...
He mentioned DFT, but then he brings in a structure that did any DFT calculation. Am I correct, right?
Well, the unlabeled part, because it's unlabeled, does need DFT. But so if you bring in some bizarre structures, I think that will break the model. So the structure should be reasonable.
Oh, she's faster.
Yeah, great talk. My question is more about when you're, like the protection of like intellectual property using machine learning and AI, especially if you're like trying to discover specific, structures and stuff. And it's obviously, or you're coming from like this plethora of information networks and libraries. How, I guess, like, are there things you can't tell the model for like, due to like things not being published? I guess it's more of like the bureaucracy of machine learning, especially when trying to like find new structures and such.
Yeah, that's a great question. I find that part a little bit, difficult to navigate. So, for instance, actually, I was talking about this William just the other day. If you have a data set that it's proprietary, and you build a model to predict things from the data set, then probably the person providing data set doesn't want you to show the model because it basically copies almost in a way in their data set. So what I've been mostly doing is usually purely open data sets and only free or open resources like Python, free libraries and so on to avoid this problem because I'm not quite sure how to deal with it.
If you want to talk with it offline after the session, we can talk about the nightmares involved.
Thank you so much for the great talk. So I was curious to know if it's possible to if I take a binary compound, for example, you can predict the formation energy of the binary compound. Mm-hmm. If I now look at different stoichiometries, there should be one of the binary compound that is more stable. And when it comes to synthesis, that's what will naturally occur during synthesis because it's the most stable of the binary compounds. Mm-hmm. So is it possible to predict the convex hull of those binaries using the model?
Yeah, people have worked on this, and I think they've claimed success when they did it, although I haven't done that myself. But I believe it is possible based on other person's results.
Yeah, so I think it will be possible because your model is predicting the formation energy. If I just focus on a set of binary, for example, silver iodide, I take different binaries of silver iodide, different stoichiometry of silver iodide. I look at it with your model and I predict all the formation energy. I should be able to find out which one is the most stable. It should be possible, no?
Yeah, I think it's definitely possible. We haven't done it yet, but it's more complicated because you have to account for different crystal structures and competing phases. So it's definitely doable. Even with this framework, you can tackle it. Mm-hmm. But so it's definitely doable. Yeah, I agree. But we haven't done it yet.
Thank you.
Yeah, you're welcome.
We have time for maybe one last.
This is a very short.
Yeah, actually, no, sorry. We have time for two.
So thank you for the talk. I really enjoyed it. I was wondering, you had this slide that talked about SOAP having 98,000 something, like that vector being that large, and then you managed to use PCA to bring it down to a more manageable number. Mm-hmm. Was there a certain is there a set variance above which you take all of those components, or is it how do you determine which components are the ones that you keep above a certain threshold?
Yeah, so I used two things. One is if you make a plot of, I don't think I have that here, but the variance versus the number of components, you'll get something like it'll take off and it'll plateau eventually. And then I think it plateaued around 550, something like that. So I started with that first, but I found that I didn't really get great model performance. So I thought if I increase it, maybe that's not going to really help. So then I started decreasing it. Then I tried different values and I settled on 220 as being the best one. So both analyzing the variance curve and then trial and error.
Last question.
So I really appreciate the talk. This was really interesting. One of the things that, at least for me, has often been kind of a question mark with these large language models is because they're these, you're dealing with really, really high dimensional polynomials. When you add or subtract one factor in your model, it can have huge effects on your predictions. So I was wondering if you or your group, or if there's some structure for kind of analyzing the stability of the solution or your prediction set. So, say you take out one of the criteria that you've used to evaluate whatever the valence structure, or you add in something which is irrelevant or is standard across. Is there any analysis to show that would preserve your prediction set, or to see if that would suddenly wildly change the predicted structures that you're about to test with experiments?
Yeah, that's a great comment. So I can tell you through a story the answer. When I first started working on this, I thought machine learning was the answer to everything. I was very, very naive. If you just use a machine learning model, you'll get the result right away and I'll be famous. But essentially, I'm just joking, but essentially what happened was nothing worked because I just tried very blindly without thinking with any my physics brain what's going to work. So I tried maybe like 100 descriptors in the beginning, and I thought, well, sure it's going to work, but nothing worked. And I thought, well, actually we're physicists here, and I think carefully what should I put into the model to make sense. So for magnetism, if I put in, for instance, the earth abundance for the element, that really doesn't really play any role, right? So then I thought, well, what's playing a role? The number of unpaired electrons, the number of d electrons. So I would put things that I thought were going to be playing an important role. And then I found that the model actually started working when I started putting some physics into the model. The other thing you can do is kind of what you already said. This is trial and error. Put things in, take things out, and see what works better. And often you can gain some insight from doing that. So let's say you take out a descriptor, which you didn't think would work really well, but somehow it tanks the model performance. Maybe that's some key to understanding the physical properties of the thing you're looking at.
And this is actually a longer discussion, right? But you could also play with how stable is your answer to the network topology, right? So some people do that where they drop out various components. They do ablation studies. There's also things like, so for example, there's a cool paper that just came out, I think it was Nature, but at least it was on the Nature podcast. But they were basically referring to something called causal tracing with large language models, where again, you try to see if you can figure out in particular which quote unquote neurons are actually involved with various concepts in the network. So there's a lot of work going on in this space, and it's also very pricey to run these kind of studies. So maybe Amazon wants to donate some credits, but anywho, we need to thank Trevor and move on. So
Thank you.
Next up, we have our penultimate speaker, or maybe ultimate speaker, Dirk Englund. So while Dirk is setting up, I'll just be very brief with the introduction. He comes to us from MIT, so not very far, where he is an IEEE fellow. Let's see, what other fellows? I think an Optica fellow, a Humboldt fellow. If you ever want to be depressed, look up his H-index. So this is a guy who has been very active, and he sort of is going to bring us back from, you've now seen an example of deep learning, and he's going to show us how we would load this onto a quantum computer. So this should be fun.
Okay, yeah, thank you so much for having me. Good afternoon, everybody. Trevor showed you the amazing things you can do with machine learning. And here I want to talk a bit about the stuff that's under the hood to make machine learning possible. And the depressing part of this talk is how intensive the compute workloads are for making Trevor's kinds of computations possible. But on the flip side, there's the physics and perhaps materials like what Trevor discovers, right, can help solve the same problem that they create. So maybe bootstrap there. Magnetic computing would be one way, right? These are new forms of computing. And I'll tell you about not magnetic computing, but one way to use optical fields to compute in a different way. That's the main of my talk, to compute. And what actually does compute mean? Anybody? What does it mean to compute? Yeah, okay, right. That's perfect, okay. I think a lot of people, in my experience, think, oh, computing means you have to implement a series of gates, let's say, right? Like one of the switches and so on, that you have to do. But that's a way of computing. But as you pointed out, the computing itself is a map from x to a function, to some map, f of x, right? And there's no prescription for how to do that, what the best way to do that is. You could, well, I mean, there are certain rules that you have to obey, namely the rules of physics and math and so on, logic. But under these rules, there's different ways you could map. Like, for example, your eyes are mapping this screen onto your retina, and for free, It's just a transformation that your eyes do. And it's a Fourier transform for free. Pretty sweet. Gives you, there you go. Are you computing? I don't know. But it is a map, right? Yeah. And so the work, like the amount of effort you have to bring up to implement a map depends on the problem, right? Like the mapping of the screen onto your retina is best done maybe using just an optical, like a lens, right? Gate-based computers can be universal. They can like perform all maps, but it's not necessarily the most efficient way to do a certain map, right? So you could have certain subclasses of problems that execute a map particularly well, and that's a subroutine of an overall process, right? And that subroutine could be realized using perhaps a quantum system or maybe some sort of a machine learning classical compute algorithm like what Trevor was talking about, right? A map from a question to an answer. And these are, actually what I'm showing you here is something that I put up here because it's actually, a lot of this was pioneered here at Harvard by Marcus Greiner and Mikhail Lukin, with whom I collaborate on these kinds of ultra-cold atom quantum computers. And this is a photograph from their laboratories. And each of these bright spots here is showing one and only one atom, in this case, rubidium, cooled to a temperature of about a microkelvin. And I like to remind my IBM and Google friends who work on superconducting quantum computers that that is 10,000 times colder than their fridge. And you can get it fairly easily just with laser cooling in an otherwise room temperature apparatus. So this is, and then you can use the internal state of these atoms to store information, like in the electronic levels, hyperfine levels. And you can read out what that information is by looking at the fluorescence. So you can see some of these here under resonant fluorescence are bright, some of them are dark. These are zeros and ones of your qubit. The part where my group comes in this is that in a universal quantum computer, you need a tremendous amount of control systems. Ideally, you would be able to control every one of these qubits with its own optical field, right? So like one qubit I could address. Now suppose I'm applying a gate, and these gates require me to switch my laser on and off in this case, to really make use of the power of this thing, maybe once every 10 nanoseconds. So I'd like some system that can project patterns of optical fields onto these ultra-cold atoms that I can program at the timescale at a frame rate of 10 nanoseconds or so, with as many spots, ideally, as many degrees of freedom, as many channels as there are atoms. In reality, you can kind of like get away with fewer sometimes. But this is all a matter of compiling. And this is why I put up here compiling. Like you have a workload and you think, what is a good way that I can compile it onto a physical thing? Right? Here's another kind of physical thing. It works in a similar way as here. These are, again, ultra-cold atoms. And what you see here on the right-hand side, these are systems that we're developing in my laboratory consisting of arrays of silicon cavities into which you can implant atom-like defects. Defects like these are, this is some sort of a substitutional system in there that creates an electronic confined structure on the nanometer scale or so within these arrays. Each of this here would be a few microns across. And the electronic levels of these artificial atoms can also store quantum information, much like you store it in this ultra-cold atom. And in this case, it's a solid-state system. So like one is, they're not as good in some respects, but the other in other respects is not yet clear what physical system we should optimally compile this workload onto. Okay, that's why we still do research. And you heard one of the speakers I saw was Marco Lonkar, and so I think he, I'm sure, did a fantastic job explaining how these kinds of color center quantum memories work. Okay, so we're at a great time, really. Like you are at a great time if you're just if you're young still, or if you're willing to switch jobs or whatever. And just it's a great time, and generally it's certainly an exciting time, because the way that we map used to be get better, sort of almost by divine law, the divine law of more, that compute becomes cheaper every year and more available, right? That has sort of run its course, and people are now looking at how can I better compile a problem onto physics, onto some physical system. And as we said already, some ways of compiling them that people are investigating, albeit not yet successfully, okay, but there's a lot of promise, is to compile onto some quantum mechanical systems. And I think you probably have heard about some of these, like these optical systems, boson sampling. Basically here, what has been shown in the last couple of years is what people term a quantum computational advantage, that at least for some problems, you can compile onto a quantum system, like of optical fields or of atoms, and obtain the map more quickly than if you map it onto a gate-based computer like what we use. So that's an example of compiling successfully a problem onto a physical thing to derive an advantage. However, the problem so far is not advantageous to us as humans. We haven't found that this kind of boson sampling or Gaussian circuit sampling is actually useful. But it's an example of like that kind of thing that can compile better. Okay, and then the other thing is we already talked, I don't need to say anything, Trevor already explained the other sort of part of this renaissance of computing that we're in, where you can compile other kinds of problems onto new computing paradigms, although they presently, the most powerful of these neural networks still run on gate-based Boolean logic. So, but nonetheless, it's a great time, I say, because we're in like this renaissance of computing where it's not just make things like smaller or something, but there's like a room for lots of ideas. We don't know what the best way is going to be. And so this is what I want to talk to you about. And so Trevor already, I missed the beginning of Trevor's talk, but I think you talked about neural networks already, Trevor? A little bit. Okay, so let me just review. So like here's the problem that a programmer like would give. And suppose this is like an image classification, so this would be an image. In this case, if it's an image, this might be a 1 million elements long vector. And then you would like to map to, what is this, a cat or a dog in this image? Okay, and you don't know the map. You don't know the map. You don't know what the compute has to be. You want to discover the map. Okay, so people have tried to make rule-based algorithms, and these rule-based human-made algorithms to discover the program that does that mapping have failed, have not succeeded, have not been good. Then in 2012, AlexNet showed that for a particular competition called ImageNet competition, that a new kind of computing that actually it's not so new, it had been around already for some 40 or so years, but now implemented on powerful hardware, could in fact discover that map. And it looks like this. So this is a deep neural network where your input is connected to the output via a number of hidden layers, each of which aggregate signals from the previous layer. And all of that is described by a matrix called a weight matrix, right? Because like, for example, the signals flowing into this neuron can be described as a weighted sum of x1, x2, x3, x4. So to evaluate this signal here, you have to think about one row in a matrix multiplying by your x column vector, right? And then the next one here is the next row of a matrix multiplied by, and so forth. So all of these weights here can be represented as a matrix connecting these to these. And so that goes through, and each of these, if you just did that, you could say, oh, I can take all of that stuff and replace it by one matrix. Okay, so the other thing that's important here is that you add this nonlinear function. So this is a function that maps an input to an output in a way that's not linear. Okay, and that gives you then the linear algebra plus nonlinear functions cascaded through this deep neural network, gives you the ability to express and approximate complicated functions. And somebody was mentioning before, like polynomial expansion and stuff like that. That's exactly what it is, right? You can, like one way to think about it is a polynomial expansion to construct these complex functions that you didn't know how to find in the first place. And so this is one way to map, but this is inspired biology, but it ain't biology, right? It's just a mathematical series of steps, and there may well be a different function to go from here to here. A different implementation, different compiling than what we show here. Okay, and so people are looking for that. This here is one like type of neural net, deep neural net, but there's many different kinds, and there's a cool sort of zoo of different kinds of neural nets that you can find on this website here. Some of them have like feedback. For example, you might have some recursion, right, that can amplify some signal and things like that. So it's really quite fascinating. People try different kind of architectures for different types of problems. Okay, so let's go to this AlexNet that I was talking about a moment ago. The thing that really showed like this stuff can really work. This is here in time, 2012, and this here shows the number of model parameters that were used in that model. So the model is shown here. It consists of a series of convolutional layers, which basically look for, like, they can discover little shapes in an image. And then out of these shapes, you can construct more complex shapes as you go down the neural net and ultimately construct a complex function that performs, in this case, the classification task. Okay, so let's see, about 100 million parameters constitute this image processing stream in AlexNet. Then, so this was a big deal. And then people said, oh, wait, I can realize the similar map, like an equivalent map in terms of error rate, using a different compilation. And that different compilation could achieve roughly the same mapping, but in a different way that was more, that required fewer parameters. So there we go. Look, there's that plasticity, right? And how you compile. What you benchmark by is how well does it do a certain task? What is the error rate on a certain task? Okay, so then people were able to do the same kind of stuff here, but in a smaller networks. But then things became started like off on this exponential scaling, where every 8 months there was a doubling of the number of model parameters of leading neural network systems. And that has brought us to like GPT-3 and GPT-4. GPT-3 and 4 have some 200 billion model parameters. And GPT-3 took 190 megawatt hours to train. And to put that into perspective, that's 20 human beings here booted up into full cognitive function at age 20, roughly. Sorry for people who are younger, but like something like that, right? And every one of these individuals is much more capable than GPT-3, but it took the same energy to train GPT-3 as it does to have 20 human beings reach the age of 20. So clearly, but the algorithms and the methods we use are vastly inferior to biology, right? So biology knows some things, has discovered some things that through evolution that we don't know. And so that's a great area of discovery. We simply don't know yet how biological machines learn so well. By the way, this is GPT-3, and I was fascinated by GPT-3. I don't know about you. Who all started working with GPT-3 when it came out, roughly? But yeah, so a couple of, raise your hand. Okay, about half of people, right? And I bet you nowadays almost everyone uses GPT frequently. Huge jump in GPT-3 and GPT-4. It's about the same number of model parameters, but GPT-4 took 60 gigawatt hours, whereas GPT-3 took 190 megawatt hours. So that's 6,000 20-year-old humans worth of energy. Wow, And is this going to stop? Probably not. So I'm showing you here a screenshot of an article I saw in the Washington Post a couple of months ago. And it said, amid explosive demand, America is running out of power. This here shows the 9-year growth forecast of demand for new electricity in gigawatt hours. Okay, so this is new electrical capacity added to our grid in North America. And it goes along. It's like, stays roughly the same. I guess this is the COVID dip, presumably because people didn't go to offices. And then bam. This is training these big AI models. That's what's driving this. And we'll see. Next quarter, I bet you it's going to be bigger still. Okay? Like the kind of scale that's being developed for training big foundation models is hard to comprehend. New data centers are equipped for some, like the latest that I heard from one of these big operators where one of my former students works. So I don't know if that's public knowledge, but therefore I won't tell you which company it is. But the number is 6 gigawatts. Right? So like a city, a big city, like Los Angeles or something like this has maybe 2 gigawatts. So it's massive. It's a massive thing what's happening. And there is probably no slowing down in the near future, other than perhaps limited resources. But Sam Altman is going around and asking folks to pitch in $7 trillion. Right? So those are the resources that we're talking about. These are like nation-state resources going into compute. Okay, so what's in the hood of these, under the hood of these things? So of course, when you build these things, you try to reduce that 6 gigawatt. Like the 6 gigawatts was not something they wanted to do. They wanted to suppress it as much as possible. How do they do that? They make custom hardware called systolic array architectures that whose function is shown here. So you have, basically, as I said, most of the compute boils down to multiplying matrices together, right, as we saw earlier. So let's say there's one matrix here. Maybe this represents your workload. This is like image 1, image 2, image 3, etc. And this here is matrix B, which might represent your model parameters at a given layer. And so what you do is you can stream here each number into this into a cell of the systolic array, which takes that number, multiplies it by the other number, which is streamed upward, right? Multiplies them and adds them to a register. Go in every time, and if you look at this long enough, you'll convince yourself that, for example, every element here, it will get all of the elements in A, and this will get all of the elements in B. And so it can perform a full inner product between two vectors. Like that vector and that vector is computed into this cell. And if you run this over all of these, then you can see that you can do lots of matrix. You basically can do matrix multiplication this way. Okay, so this is called the Tensor Processing Unit by Google. And if you go on Google Cloud and want to compute something, your compute load will likely run on these TPUs. And they are very good in matrix multiplication because they minimize the movement of information. And this interconnect energy tends to be the dominant energy in compute loads, both for training and for inference. So you want to basically take every element here of this data and move it as little as possible. And you do that here by tiling it so that this guy can do this thing and then it moves over one cell and so forth. This is quite good at minimizing data movement. But despite all of these optimizations, chips are still dominated by data movement cost and not the raw processing of the transistors that are necessary to implement binary Boolean-based multiplication.
So is that data movement on TPU or data movement between CPU to TPU?
On the TPU itself, okay, you minimize it. You minimize it by having data, like here it's used to calculate this part. Then the same data is used to calculate this part, etc. Right? So you do all these tricks and still the energy consumption is dominated by data movement. And one of the reasons you can see this is that if you want to retrieve some model parameters from memory on a computer, you will have to access some, typically for these larger models, sufficiently large memory, which tends to be not in the chip, but off the chip. And accessing 1 bit from an external memory on the board level costs you about a picojoule. Okay, because that is a thing, there's a processor in and of itself and has to do its thing to find the addresses and stuff like that. It takes about a picojoule. And so, so the key lesson here is that there's 2 key limiters to the tensor processing unit. One is power, which leads to heat dissipation, and then that limits like how much compute you can run given a certain resource, because eventually it gets too hot. These things are already running hotter than like your stove. And the second is the interconnects and data movement. Okay, so key point number 1 I want to drive home here is that you should try to use data fan-out for free data movement whenever possible. Look at this. This is an image of one of these data centers. Okay, this is a normal-sized human being, so these things are massive. And on the rack are these machines, these tensor processing units. And what are they doing? They're processing like image recognition or some other set of workloads, and the set of possible workloads is the finite set. It's a relatively small set of workloads that they perform. Okay, so it seems kind of crazy when you think about it that all of these processors, even though they're computing the same model, they're retrieving their same data from memory. Why don't you have one central server that supplies them with the model parameters? Then you only have to pay that 1 picojoule per bit of energy per retrieval for memory once, and you can supply lots of computers that are doing the same compute task with the model parameters they require to do what they need to do. Okay? So that's called disaggregated memory access. And that's one example of a big opportunity by which you could significantly reduce the energy consumption of data centers. But it requires new technology to be brought into the chip level. And that technology, one of them, the leading one, is optical interconnects. So if you have a way to have a server stream out model parameters, you can amortize the cost of model parameter access by distributing that data across many client servers that compute on it. But you have to get that data into the processor. And if you look at like an NVIDIA machine, the processor, there isn't very much space there. And when you talk to NVIDIA, and companies do, hey, you should like change your architecture, they have to do a lot of trade-offs themselves. Because, for example, if you let optics in there that consumes, like that takes away copper, then the chips may not be able to run as fast because you can't remove as much heat. And so there's a bunch of trade-offs that the folks have to deal with. Okay, and that's one of the barriers to make this happen. So as the new technologies have to be invented and cooperation has to happen. But even then, you say, suppose you can get all that data to your inference machines on these racks. Is that enough? Because they're still using that data in the same way, still as gate-based compute engines, Boolean compute engines, conventional way. Whereas this machine works in a completely different way, right? Spiking-based. This is spiking-based neural networks, and these we know from a moment ago that these we all know that it's like that is a much more efficient machine at learning. This machine here, than this machine, like vastly more efficient by orders of magnitude, probably a certain tasks. Okay, so that's non-Boolean logic. Where it's like, so this one is definitely the winner in like doing Google Sheet computations. Although I did try that with my son, it didn't work so well. But on some other workloads, like the biological brains are vastly better still, right? So like, what is the best way to map your compute onto biological brains, onto these Boolean machines, or onto something else, some neuromorphic machine, or perhaps a quantum computer, we don't know. And so one way to find out is to try. Okay, and so this is what we've been doing in my group for the last 15 or so years, to try out different architectures, and I want to give you here my lessons learned thus far in this. So, but before I do, I have to give credit to where these ideas actually come from. What I'll show you is the second incarnation, or sometimes third incarnation, of ideas that had been around before by people who who did the stuff before us. So Dimitri Psaltis and Ravi Atale, for example, did a lot of the early work looking at this kind of distributed compute load and with optical neural networks, where you'd say, okay, suppose I have some transmitter of my workload, X, over expressed on an n-sized vector, and then I have a weight matrix that does n by n, that is in size n by n, and I need to compute the inner product between, the matrix product between this input vector X and the model matrix W to get my output. That's the output that then goes into a nonlinear function, right? And so we already talked about a moment ago that, hey, your eyes do a Fourier transform for you for free. So we know of like optical things that do some form of computing for free. And if this weight matrix happened to be the Fourier transform, you would be set. You just use a wet lens for this and it would work. But it's not just it's not just a Fourier transform. This weight matrix needs to be like more controlled. Okay, so that's the rub. So you need to sort of devise materials or methods by which you can implement optical transformations on fields. But if you can do that efficiently and with high fidelity, then you can compute for free. You compute as much energy is needed as your eye looking at the screen. Nothing. Okay, at least for that part. Okay, so that was the idea, and they actually did beautiful work back then, but they didn't quite have all the tools in the 1980s. Nowadays we have new tools, these photonic integrated circuits, that allow you to perform high fidelity transformations on an input going to the output. And this is one of these things here. This is a photonic integrated circuit that we developed at MIT, actually for a reason not connected to machine learning at all, but for some quantum optics. And but it actually turned out it was fortuitous. It worked really well for doing these kinds of matrix transformations. So what you have here is a number of waveguides. It's maybe you can see it kind of, there's like 26 lines going in on the left-hand side there. And in these 26 lines, you can encode a 1 by 26 vector. Okay, and then this thing here consists of lots and lots of like Mach-Zehnder interferometers, which are little controllable switches that allow you to send light either up or down between two inputs and two outputs. And we tile them in a way that by the combination, if you calculate the settings on these Mach-Zehnder interferometers, by the combination of them, you can make use of this mesh, okay, these cascaded Mach-Zehnder interferometers, to program a particular transformation, which I can represent here as a unitary transformation, a matrix that acts on n inputs and gives me n outputs. All right, so that solves the problem that the 1980s folks had to some extent, because you can make use of these programmable circuits as high fidelity matrices that store your model parameter, and that then allows you to input your task, okay, and perform this weighted product. Okay, now the trick is the following. The thing is that how much energy is needed to perform this transformation if you encode the input vector, send it through, and then sample the output vector. For n channels, the amount of energy you need is you just have to encode n signals. This here stays stationary So the energy needed to perform a matrix vector multiplication on this machine is of order n. Whereas, right, in a conventional Boolean computer, you have an n by n matrix multiplying a 1 by n vector. The amount of compute you need scales as order n squared, because there are n squared elements in the matrix. So there's a difference in scaling. One is order n amount of compute, the other one is order n squared compute. So this is an example of in-memory computing, and that has been done already also in electronic machines. You can use resistor networks to program the weights and then flow the current through them and use that as a way of computing these matrix vector products. But in both of these cases, they're neuromorphic computers that have a different scaling behavior, and thus when you look at the way, like, I can map this problem onto this physics, like this neuromorphic machine, or that physics, a Boolean von Neumann computer architecture. In this physics, that particular workload of looking at matrix vector products has fundamentally different scaling behavior in its effort than that one, right? Fundamentally different. So doing the same stuff, but they're fundamentally different in their intensity of energy use. I'll show you another example here of this kind of a physics-based compute that relies here on something that many of you will take for granted, and it turns out it's quite powerful. And this is a homodyne receiver. So homodyne receivers are used for coherent communications in the internet. They're commonplace. And normally what you do is you take an optical signal, which might carry your information, and you, in a homodyne receiver, you mix it with a local oscillator. It's also done in your phones, by the way. When you have on your cell phone, you have a local oscillator operating at 2.5 gigahertz or so. There's some signal coming in from the transmitter, and you mix them locally to bring them down near baseband. Okay, so demodulate them. So that's the local oscillator. It's a conventional thing. This here would be normally the local oscillator. But what if instead it's not a local oscillator, not just a sine wave, but it's a modulated sine wave to encode some other information? Then, if you do the math here, you have, like here, after this beam splitter, you have x1 plus w, and here x1 minus w. Absolute value squared is the square law on the photodetector. Take the difference on a differential receiver, which is commonly done. And what you have is the inner product is just the interference term that remains between this field and that field. And that interference is given by that term, the amplitude of it is x1 times, is x times w, term by term. Voila, you have a product engine, and it works by itself. It's just the physics is doing what it does. It requires no energy consumption whatsoever, because that receiver there, that photodetector, can be a photovoltaic device. It might even give you a little bit of energy, look, you know. And it takes an inner product it takes a multiplication between two scalars implemented here in these two fields, all right? And then the other magical thing that happens is if this, like each of these pulses here, suppose it's 1 picosecond short, super, super short, okay? Then 1 picosecond later, another pair of pulses comes in, they do the same thing. And what happens to the photocurrent that comes here out of this differential receiver? Well, it adds if it's connected to a capacitor. So you integrate, and what you do, and therefore, is the sum over all of these channels gives you the dot product between the two vectors. Okay, so look at that. You can perform a dot product between two n-sized vectors for free, not quite, because ultimately you have to sample the capacitor here, and that's a one-time cost. So the effort scales as one. So this is another example of the same thing I showed you before, but now looking at just inner products between vectors. So on a physics, when you compile onto this machine, the problem of finding inner products between two vectors, the effort that machine has to extend scales as order 1. It's independent of the length of the vectors. Kind of crazy to think about, but that's true. So this is you can compile that workload very well onto this kind of a machine. It's fundamentally better than a computer, with a Boolean computer, which would require of order n operations to do the same workload. Okay, so now we can take that principle and fan it out and so forth. And then you can convince yourself, it's fairly easy once you understand that you can run stuff in parallel, and you can do a matrix vector multiplier by the same principle, okay, but now with many receivers, n receivers, okay, and now you have the same advantage of order n amount of effort to compute a vector matrix product versus on a von Neumann machine, order n squared to perform the same map. Okay, and this is, I'll show you the sort of the remarkable thing about this is illustrated here. So this is plotting, if we take the values of today's hardware and we calculate, like if you built a supercomputer based on this type of compilation, and you have, for every layer, you have this number of neurons, okay, 100, 1,000, 10,000, etc. And you compute what is the energy that a von Neumann type of computer would have to extend per multiply accumulate, or MAC, to keep up with this kind of physics-based computing. That's shown here. Okay, so here's current technology and so on. So like right now we start out here with you'd have to extend about a picojoule per bit for very small workloads. But for all of these lines, because of this n squared versus n behavior, you actually, like the amount of energy that a conventional computer would have to extend per multiply accumulate to keep up with this kind of a machine is shown here, and eventually it dips below the Landauer limit. So this means that a machine based on these principles could compute at an energy consumption that for a conventional computer to match it, it would have to break thermodynamics. Okay, so that seems crazy. How can that be? Well, it's because we compile it onto a different machine. And like we said, like you can compile workloads onto different types of machines. Some of them are better for certain things, some of them are better for other things. This is particularly good. This kind of machine is very good at the problem of inner products between vectors. And moreover, since the energy needed to do a nonlinear transformation also per neuron scales as n, and we know that we can construct any function out of a series of like the thing that a deep neural network is capable of approximating any function that you can run on a classical computer. That means that this is universal. So you could in principle derive a universal gain, not just for machine learning workloads, but for other types of workloads too. So that's what the physics says. And the key lesson here, number two, is in physics computing allows you to compute at a fundamentally different scale for certain workloads. Okay, so that's pretty interesting. And so far we haven't been proven, like so far a lot of work by our group, this was a theory paper from our team, and since then a number of groups have actually have shown that this is true. Okay, but it's not yet in the data centers. So there's some obstacles that we need to still overcome to understand if this is really viable. And one of them for analog computing that should always be careful about is errors. This machine is amazing, the difference engine, the Babbage difference engine, but it didn't work well enough. In other words, the error rate for certain workloads was too high to make it useful. This is a machine invented at MIT less than 100 years ago. And it too was based on a sort of neuromorphic principle. And it's called the continuous intergraph, okay? And actually it's cool, when you read the abstract from this 1927 paper, it says, the intergraph has been developed, which plots continuously the integral of the product of two functions. Look, it's doing inner products. It uses the principle of electrical integrating, blah, 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 okay? Look at this, errors of the machine have been reduced to an average of 1% for common uses. What they did then, this is Vannevar Bush, who became famous afterwards. He was advisor to the president on science matters and stuff like that. What they did is they did empirical benchmarking, just like what we do nowadays with quantum computers. They didn't know that this was a universal machine, but they just did empirically, like, is it useful for certain things? Yes or no, right? So, but this thing never really, beyond, like, then the digital revolution came and this thing fell by the wayside. But it was, as far as I know, the first computer that was actually produced in multiple iterations that people actually paid for. So it has use because the market says if somebody pays for it, presumably it's useful. Okay, so economics said that that thing was actually a useful machine. All right, so the errors. The errors are a tricky thing, and we have to make sure that our system isn't going to be limited by errors. So I'm going to just, because of in the interest of time here, to catch up a little bit, show you. I'll just skip over this part here, and I want to get to this. So I worried about that tremendously if these machines would be limited by the same errors. But it turns out there's a fundamental difference between a mechanical machine at room temperature, like the one we saw earlier, or an electrical machine that also is dissipative, like the other machine that we saw earlier, the Babbage difference engine and the continuous intergraph, respectively, and optics. And the difference is that errors in an optical system, when you build an optical system, and there will be some differences compared to what you wanted to build, those errors on the optical fields are coherent. So you might have a phase error. So optical field flows through a path, and then there was some defect, so there's a phase on here. Okay, well that you can cancel that phase. If you know that there was a defect there, you can undo it. And this is possible when the thing that carries your information, in this case the optical field, has long coherence. Okay? By contrast, the other machines have short coherence. When an error happens, it dissipates to the environment and is irrecoverable. Here, it's just a phase error that you can measure and subsequently correct. And in a series of papers, we were able to show first that we could cancel errors in the small components that constitute these machines. And after a number of papers, we arrived at this result, that when you make these kinds of optical meshes, it is possible to, when you have a big enough mesh, you can perform these matrices in a way that's asymptotically fault tolerant in a programmable way. And the way to think about that is if the mesh, the thing that, like the circuit becomes large enough and has sufficient number of degrees of freedom, you can always cancel coherent errors. Okay? And that makes it, so that for us was, okay, green light, let's proceed. Right? These things can actually be useful. And so here's one of these devices that we then made, and this is a paper here that's soon to appear in this publication by Shamil Bandyopadhyay. And I show you here, like what I said is you have to encode a problem, then do the matrix multiplication, the nonlinearity, and repeat through multiple hidden and ultimately the output layer. So you need all these elements together, and although not necessary, it's nice if you can do it on one machine because then you have the advantages of very low latency. And here's the machine. So here's your input, and the optical fields go through a number of input and hidden layers, etc., and nonlinearities, and the receiver. And this thing can actually do certain classifications. And crucial to making this machine work was that we developed a programmable inline nonlinearity. The nonlinearity we said was necessary in these kinds of architectures. And we're able to do that by, you could do that in a way using some nonlinear optical material, but nature isn't kind to us with nonlinear optical materials. They're fairly weak. Okay, but we can use our engineering. You can take a photodetector, which is extremely nonlinear on the optical field, and then it collapses it, and use it to charge a capacitor, which modulates an optical field through a resonator, for example. That's an engineered nonlinear. It turns out to be a chi3 equivalent sort of nonlinearity, like a Kerr medium. And that can be very efficient indeed. And that's what we used in this paper. So for detail, take a look at the paper. So that was a big thing for us. Now, suppose that I gave you, actually one thing that was important. When Shamil tried to run some workload, he first took the good old MNIST data set and stuff like that off the internet. And we tend to try those things first. So we try to compile the workload of the deep neural network onto the hardware. But that workload was optimized for a von Neumann computer, not for that computer. So he never could get it to work so well. But then we did something different. We said, what if we have that machine train itself? And that's what we do in this. This is part of that paper. So we use basically a gradient descent method, a variant of that, to teach the machine itself. Yeah, Tina?
Just to help us put in context, can you tell us the overall size of this machine?
Yeah, this machine comprises a few hundred, about maybe 400 degrees of freedom or so. Yeah, and the size is a few millimeters square. Yeah, right. Yeah, yeah, right. I mean, right. It's still it's a very baby thing. It's like a little like amoeba kind of equivalent that you train to do sort of to avoid, to like sugar and avoid poison kind of this. You can do that. But suppose that you've trained that machine, right? And okay, I've like brought this machine up. This is now trained to do a certain thing. I thought, well, what if I wanted to train the next machine? It has slightly different errors. It's fabricated slightly differently. Every machine by this analog way is a little bit different. Does it mean that I have to rear this other machine? It has to also go through kindergarten, high school, etc. Do I have to train every analog machine individually? And interestingly, the answer is no. So we developed an algorithm that's a theory paper published here that showed that if you make the brain a certain architecture of this kind of an analog machine, then any errors that you have in the fabrication of this analog machine can lead to small and correctable perturbations on its function. So you can download the same program onto the next analog machine, and it will, with a small order n optimization, which is very short, be as capable as the first. So once you've trained one, you can actually copy its brain onto the others. We take that for granted for digital, like von Neumann machines, right? But it wasn't clear that the same would hold for analog machines. Certainly doesn't hold for these analog machines that we have, right? But it is true if you architect things a certain way. And so that paper was here, this transferable learning. Okay, so in situ training is possible. All right, so now the last thing I want to tell you about is to go back to the very first point of you should do fan out when possible. So I'm going to ask, hey Google, what time is it?
It's 3:16 p.m.
Hey Siri, what time is it? Hey Siri, what time is it? Wow, okay. So it sounds like the voice recognition by Apple is better or something. Or nobody here has an iPhone, which I don't think is the case.
I was trying to help you, but you went too fast.
Okay, so it's also, yeah. So, but the thing I wanted to point out is the lag. There's a latency. Why? Because what it does when you ask it that is it takes your voice as a WAV file, it sends it into the cloud, processes it there, like with the data center we showed, then it sends it back and you do the rest, right? So it delegates the workload of language processing to a more powerful computer in the cloud. That's because that is already a hefty workload, and you want to preserve battery and the smaller processors and so on locally. Okay, so what machines do nowadays is they delegate to the cloud these workloads. But as we said, we could stream the model parameters out, and then we said that the inference machine could be very low energy, and we showed that here that this is in fact the case. So we had a transmitter that streamed neural net model parameters across the metropolitan scale of the Boston area. The transmitter was located at MIT Lincoln Laboratory, and we had a client that was listening to the model parameters and had some local buffered workload, and used it to do this matrix vector multiplication by the method I showed a moment ago using the Homodyne receiver. So you can look at the paper in detail for details here, but the point is that the inference accuracy was equivalent. However, the energy needed to compute for that type of distributed architecture on the client side only was about 3 orders of magnitude lower. So we could compute with 10 milliwatts what it normally takes a NVIDIA machine with 10 watts to do. And that's the power of these computing and compiling onto the hardware in a different way, right? It can't do everything, but it can do that workload very, very well. In fact, surprisingly, maybe initially, but then it makes sense when you think about it, on every transmission that has one model parameter that it sends to the client, the number of photons can be much smaller than you would at first expect. You would say, oh, I have to have low bit error rate. That's not true. What you have to have is low bit error rate in the aggregate sum of n transmissions. And per transmission, per model parameter, the number of photons can be of order of 1 or even less. So this is the accuracy. So basically you saturate already. In this case, we were able to saturate on the receiver side with just of order of 1 photon per symbol, right? So the shot noise is huge. But because we're not asking about shot noise, we're not asking about what is the value per symbol, but we're asking about what is the integration of n symbols with an n-sized problem, the bit error rate can be very small. And so, so then here's just along the way, you have to develop new kinds of hardware, even like new architectures here. This is thin film lithium niobate, and here is silicon photonics that, you have to make this work, to solve these kinds of problems, you have to develop a lot of new stuff, both on the algorithmic side, on the modeling side, and on the hardware side. And one of the actually really highlight papers from my team was by Ronald Davis. He just put this on the he just resubmitted this paper, and this is showing a different kind of compute that is it's more spatially efficient. It encodes not in spatial domain, as we saw, but instead in the frequency domain. And there's plenty of room in frequency. As Feynman said, no, he didn't say that, but he said plenty of room at the bottom. There's plenty of room in frequency space, right? So if you, and that's what Ronald did in his PhD work. And so that paper is, it's soon to be uploaded on arXiv. It's a really important result by our team. So I wanted to, then what if the state of your system could be in superposition? And this is sort of like what I hinted at the very beginning. This becomes possible when you use these optical, linear optical systems, but you couple them to something that can be in superposition. One way to do that is to take these, like a reflective surface, for example, and couple it to spin states via a spin photon interface that's realized by the electronic transition, the transition between electronic levels in an atom-like system. So there's work that we're pursuing in that direction, and that could allow for new kinds of machine learning that does what we talked about so far, but rather than instead of at every neuron, you compute the inputs and put that neuron into a definite state, you can put that neuron in superposition through the whole layer. And that kind of machine, called a quantum neural network, could be a new way of training computers despite internal flaws that they have, because you can just, like what I showed 5-10 minutes ago, you could, the machine can train itself and in this way undo its errors or mitigate its errors. This brings me to the summary that the key points I wanted to tell you about is, when possible, try to use data fan-out. In physics computing can allow for more efficient compilation. Coherent cancellation can cancel errors. So these machines can, in principle, scale. And in situ training allows for a new way of training of machines that in our experience so far is more efficient, but we don't know what it is, how it will turn out at scale, right? If we can help mitigate this problem that we talked about at the beginning, we don't yet know. And some of the spin-off companies from our team at MIT are trying to find that out by actually building large optical machines. This is called Passage. This is by a company that was created by two of my PhD students called Light Matter. And they're building optical compute systems that, optical substrates that allow NVIDIA and the like to compute in, to at least do the information movement more efficiently. And just sort of in closing, along the way, when you solve these, when you take on these really tough things, if you do a tough thing, if you look at something that's really difficult, and even if it's sort of incremental progress on it, it tends to open up new opportunities and insights. So I generally tell my PhD students, like, let's take a really tough problem and if you make an incremental advance on a tough problem, much more important than if you do a home run on an incremental problem. And we've seen that work lead to a number of companies that are actually in the space of sort of deep tech and trying to solve some of these problems. Most recently, axiomatic AI, where along the way of doing these things, we realized over and over again, we really need to be able to compute through design engine and physics decisions. And that has been a big problem for us in all of these endeavors and in the research group. And so actually generative AI, and this is again where this bootstrapping comes in, generative AI might be one way that you can use generative AI to make the next generation of machines better, but also in a way that doesn't destroy the planet. So with that, thanks a lot for your attention and questions. I'm happy to take some last minutes.
So thanks for a fun talk. Maybe I'll take chair's prerogative and ask a question. Maybe it's a two-parter though. So the first part is, am I right in understanding that the topology of your network is fixed? So it's like you implement, say, some version of ResNet or LaCoonNet, and then you're kind of done. And then if somebody wants to change the network architecture, then that's a new chip?
Yeah, so the chips are programmable. So in principle, you can dice up your problem into the weight stationary architecture that I showed a moment ago in sort of like more arbitrary ways. You can think of the whole thing as you can take a big matrix and compile it and cut it up into smaller submatrices and then run them on a given size processor.
But now I have to go each
Yeah,
time, right?
but that said, actually, what we at MIT are chiefly pursuing is the coherent multiplication. In the case of the second example that I showed, this homodyne receiver-based machine, it is fully programmable. You can compute extremely large matrices together because the longer you integrate, the greater the inner product of vectors that it can compute. Right? So there's no limit. You can have a billion size inner product. You can make an inner product between two 1 billion sized vectors, and it's still of order 1 in the workload.
Okay. Have to think a little bit. Okay. Let's see. I'll open it up to others, and then maybe I'll come back for mine, just to be fair. So we have a question in the back. Do we have a microphone?
Hi. Great talk. My name is Charles. I'm actually a computer scientist, and I'm in high performance computing. And you showed some instructions. So standard CPUs, it takes every instruction takes a number of clock cycles to perform the operation. What kind of latencies are you seeing? Because you've covered Moore's law, which we're hitting, as well as like the power wall. But performance matters in terms of speed up. So what kind of speed ups are we seeing as well as?
Yeah. So it's really we're showing these systems work in different proof of principle studies that explore different aspects of that type of compute. Okay, latency example, paper that we published that first author is Leanne Bernstein, and it was published last year, I think, in Science Advances, showed that the latency on a on a matrix product could be as little as sub-nanoseconds. Okay, the caveat, however, is that it takes us a long time to encode the next problem, right? So there's a bottleneck, right? But the physics says you can do, actually, it turns out like picosecond, sort of like is the duration. We showed it down to 60 femtosecond, actually. So you can compute some things very fast, but then there's a lag to do the next cycle. Okay, so that's like latency can in principle be super short, right? And then in a different paper, in a different work, we study, let's say, the energy per Mach, like that it can be like below, people have shown that it can be basically not achievable by conventional machines, the energy per multiply accumulate. But what you have to do to really translate the possibilities into actual utility is bring all these things together into one machine. And that remains outstanding. Okay, but a great question. Yeah.
Right. Let's see. Sarah. Okay, we have one over here, but I guess she's over there. But then it gets next one here.
Hello. Since you seem to have a really good grasp on all the different types of computing, including analog, do you foresee a future where perhaps computer architectures are some combination of different types of computing? So when it comes to my head, the thing I could thought of is we could keep our classical smartphones, not necessarily have to have a quantum smartphone, but through cloud computing, we could then also exert and send it to a quantum computer where we could get that delay that you've demonstrated reduced to some extent, right? Yeah. And so how complex do you think we can get in the terms of computer architecture, as I'm taking a class in the subject right now?
No, it's a great question. Already today, there's a great deal of specialization in the computer hardware, and TPUs and GPUs are just one reflection of that specialization. We don't do everything anymore with CPUs. Obviously, you cover that in your thing. So I think that one can expect that there will be more specialization, because when you have large systems, it can pay to break them up into smaller, tailored subunits. And biology, again, actually is a good example. There are specialized neurons that I think it's worth looking at biology, and probably the same will hold here.
Okay, thank you so much.
Sure.
Wonderful answer.
So we'll take one last question over here, and then we'll move on to our closing.
Okay. Thank you so much for a great talk. So I was wondering, with an analog machine, so I will imagine that we'll have issues regarding stability. So how do you know your machine is not going to have some chaotic behavior? That's my first question. The second one is, how do you deal with errors, right? And did you do any cost analysis in terms of error correction? Mm-hmm. How much will it cost?
Yeah, that's a great question. So number one, stability. So in a binary computer, you can tolerate a great deal of fluctuations, right? Because you can still differentiate what's a 0 and what's a 1. But actually, a number of conventional computers, even von Neumann types, used more than 2 levels to encode information. An example actually is the first useful transistor vacuum tube computer called the ENIAC. Yeah, somebody's nodding. Do you know how many levels it used to store information? What's that? No, actually a bit less than that. The number maybe we're talking about slightly different things, but the number I remember is 4. So the first digital computer used 4 digits. It was using not binary, but using 4 digits. So and then in your smartphone, the information is sent to you in alphabets that comprise, I think, 256 symbols nowadays. So so we see different, like on the encoding side, the constraints of the engineering problem move you to encode in different ways to maximize your channel's utility given the constraints. And that can sometimes mean you do PAM4, that's 4 levels, or you do 256 levels, like in a cell phone, and sometimes just binary levels. These are all possible. And then when actually people talk about in analog computing, it's continuous. Actually, I kind of take issue with that. I think that's not really true. Analog computing is also kind of a misnomer. It means like computing by analogy. But it's continuous, okay? But in reality, what we do in our analog systems, actually, we don't treat them as analog systems. We treat them as large alphabet, like multi-level systems with something like, in fact, 128 is what we often do. So it's really, there's a continuum, I would say, between binary encoding and n-ary encoding with, and then you can, that's again the compiler problem. It's a compiler problem at the end. But it's a great question. And then the second one was error correction. So once you work on a discrete space, you can actually use more conventional error correction methods, right? Because you can use like Reed-Solomon code and so on discrete levels.
All right, so with that, let's thank our speaker. And we'll see if Bill has his voice back.
So I say all the time, I enjoy listening to Professor Englund, but he scares me to death. Especially the notion of AI training itself and then training other AI. Sounds like Skynet to me all over again. So again, I apologize for the fact I've lost my voice over these last few days, mostly yesterday. But I just wanted to start to thank some people. First, I want to thank you for coming and being a part of this. I need your survey results more importantly, because I want to know how to do this better the next time. And I want to learn how to do that from you. I thought the easiest way to kind of thank the folks on the committee was to show you where we started. This is the outline we started with in our first conference call. And we broke everything up into subject areas. We threw everybody on the list. Most of these folks have been here over the course of the last few days, and everyone was instrumental in using their time, effort, and brilliance in moving this project along. And thank you all. And of course, their work is not done. I also want to thank our sponsors, National Science Foundation, NSPP, all the people I beat up at Harvard for money, particularly the Harvard, the Science Division, SEAS, the Harvard Quantum Initiative, Harvard Physics, which gave us all of their facilities, and my partner in crime at CNS, Bob Westerveld, Professor Westerveld. Of course, all of our speakers. As I mentioned, we will have most of the talk recordings kind of online, probably by the end of the month. That'll be the goal, to have them linked to the website. And to the extent that I can collect them, I'll try to collect as many slides as I can and put them also on as part of the repository. But we thank all of them. And the reality is that amazing people came to talk about amazing science, and everyone was really excited to do it, in part because of the nature of the meeting. And then last but not least, I want to thank my local team. Linda, who's not here, I don't think. I think Jared is hiding in the back. Jared is the guy who made sure everybody had a hotel room and a place to stay. Damon Mannings, I think Damon had some work to do at MIT today, so he's not here again. Also, part of the core team, Cassidy, who helped work the registration desk, and then all of our students from NSPP, from Harvard and MIT, Makunde and Nicole in the back. And yes, I'm going to hook you up with baseball jerseys. You just got to give me your size. And then last but not least, as I said, I want you guys to help us define what's next. So, of course, the survey. And I remind you again, this is what we got to look up to here. So, your work's not done either. And so thanks, everybody, and have a safe trip home.